All right, here I'm going to show you some of the steps of getting your structure from the journal article and then opening it in Mercury and some of the manipulations you can do in Mercury. Once you've found the article that you want, most journals, this is inorganic chemistry, but they all do this. Most journals have what's called something like supporting information. In other words, extra information that is not in the published printed article. This is extra information deposited on the file. This is where your CIF file, crystallographic information format file, will be located. And it keeps changing about every 2 years. They keep changing the format. So if I click on this, if I go over here and look, you can see, here's an example of what they're talking about. Cambridge Crystallographic Data Center, the journal article, the people who published this paper deposited the structure of the compounds that are used in this paper at this file. So you'll find something that looks like getting you to the CIF, okay? I'm gonna click on that. That's going to take me to the CCDC where that particular file is located. And I know they say, well, there's a viewer right here. Why don't we use that instead of Mercury? Because it's not as good as Mercury. It'll give you a quick view. But what we want to do is we want to go to download. We want to download the current entry. So for example, this particular structure from this paper, choose the current entry and you'll have your information in there. And what we're going to want to do is we want to download the deposited CIFs. Now, this was a slow download. It took a while, so I've already downloaded it on another tab, and I'll show you what this looks like. But you would click download and you wait, go get a cup of coffee and come back 5 minutes, and you'll have had the structure. Okay, once you click download. I've already done that. Here's my download. Because I have Mercury on my computer, Mercury will open it automatically. It seems like Mercury is out of date about every 5 days. So it'll say that, but you can still step into your structure. And this is one of the structures from the paper. Occasionally, you'll see 3 or 4 listed here. Like sometimes there'll be like 10 compounds in one structure. And you don't need to do all 10. You just need to do one, pick the one that's interesting to you, and you click on it and it will show you. So if you had more than one, you'd see it listed here. There's only one structure here. This is that notation I said, the information about the unit cell. This is C2C, okay? C is like P, like F. It's another notation that's indicating the symmetry of the unit cell. This doesn't look like a unit cell because all it is the structure of the molecule. So once you have it up, you can, of course, save that CIF file. I would encourage you to save it to your hard drive so you can open it and do whatever you want with, whatever you want with it. But one of the first things I do is I turn off the hydrogens, which are the white ones, because they just get in the way, okay? So you'll have to use your knowledge of carbon to know that there are hydrogens on some of these carbons, okay? One of the interesting things that you'll see is occasionally you will see these extra atoms out here, and you'll see the ones that look weird. This is a case of sometimes in crystallography, the atoms are blurry. Their actual position from one unit cell to the next can be indistinct. And so what you get is you get some sort of an average of the two in your experiment. But here are my atoms. Right now I'm under pick atoms, and so I could pick an atom and it could tell me what that is. I don't have my labels turned on, label the atoms. Okay, that's manganese right there, apparently. I can click on that. That should be an oxygen. I can click on that one and I'll label the atoms. Those are oxygens and so forth, okay? So you can click off all those and we turn the labels off, okay? Hide the hydrogens. What if you want to change the style? What if you want to be something like, this is thermal ellipsoid, and we won't go into this, but the thermal ellipsoid has information about the crystallographic average position of that atom in the structure. So we do ball and stick. There's the classic ball and stick. You can do space filling models and you can turn them around. I found out that you can zoom in and out with the right mouse button slid up and down, zooms it in and out, okay, right? So let me go back to my ball and stick. Now what I want to do is I want to do some other things. I might want to show the unit cell. So I go down here and I choose show the cell axis. If this menu is not open, okay, it's up under your display options. I forget which one, but there's a display option which would allow your display options to be a menu down at the bottom. Remember using the right mouse button to back up my unit cell. And if you look, so, well, that doesn't look like a unit cell. I only see one form of the molecule. Okay, get ready. But see how this unit cell, the angles are not all 90, are they? Okay, so the alpha, beta, and gamma will be something other than 90. Okay, I will label the atoms. I need to label the atoms. But what else I could do is I can do something called show the packing. This will show the packing, and it will literally show, and then you want to get something busy, it will show you literally what this solid would look like if it was packed into the unit cell. So if you added up all the parts, you would get the total number of molecules within this unit cell. Turn it off because it's incredibly busy, right? I can show the cell axis if you want. Okay, what are some other things you can do? I'm assuming you all know how to take screenshots, so I know you can rotate screenshots. One of the things you can do is you can view it along A. This is looking straight down the barrel of A. You can view it along B. It's looking straight down the barrel of B. And you can view it along C. So you can see that some of these angles are 90. Some of these angles are 90, but one of the angles is not 90. And this is something that people will refer to usually as monoclinic. One angle, not 90 in this case, right? I want to show you one last thing, and that's determining the powder pattern, okay? Bear in mind that when people determine the structure of a molecule, one single molecule, you need a single crystal that you subject to X-ray beams, and you work backwards on the X-ray diffraction pattern. It's some very interesting physics and physical chemistry to work backwards, and you can get very, very precise, better than NMR, better than any structural tool you can use. Crystallography gives the precise distances and bond angles of the solid, of the atoms in the solid, in the molecule. The only downside is this guy has to be a solid, because you can't easily do X-ray diffraction because there's no regular pattern if it's a gas or a liquid. It has to be a crystalline solid to do this. So lastly, let me show you what we do for a powder pattern. Powder pattern, you know what, they're under calculate powder pattern, okay? So even though, let me blow this up, even though this crystalline solid had a structure determined by single crystal X-ray diffraction, if I took those crystals, or I made a precipitate, which would be a powder, and laid it out on a microscope slide, and I measure the diffraction off of planes, off of the powder that's on that slide, what I get is these peaks. And notice that these peaks occur at values of 2 theta, okay? That's referring to the angle that the X-rays are incident on the powder, on the microscope slide. One of the neat things about it is if you want to, you can zoom on a part of this. And what you get is you get peaks. You say, well, those are spectral peaks. Those are not spectral peaks. Those are reflections. Those are the cases that every one of these peaks is a case where the Bragg condition, the diffraction condition, gave rise to constructive X-ray interference and gave rise to an X-ray spot on the detector or film back in the old days. Now watch what happens. If I mouse over these, see how the HKL values are changing. Literally, these are reflections off of different planes of atoms, okay? And you say, well, I'm not sure what the 111 means and the 21 and all that other thing. But we won't go into it in this class. But people that do crystallography will know that these H, K, and L are what are referred to as Miller indices, and they refer to the indices of the planes that are slicing through that crystalline structure. So you could imagine, go back to our powder, or let me turn this off, go back to our packing picture. You can totally imagine, if I put that back on, some powder pattern, not powder pattern, that's not what I want. Packing is what I want. Packing and slicing, okay, make packet. This is kind of a messy structure, so if I were you, I might pick something that's a little bit not so bad. But you could totally imagine that slicing through this unit cell in all directions and all different orientations are planes of atoms. And it is as that crystal is rotated through the X-ray angle, you get diffraction and no diffraction, diffraction, no diffraction, diffraction, no diffraction. So let me go back to the powder pattern one more time just to point this out. Let me zoom in on a part. That means that at this value of 2 theta, which is what, 10.391 degrees, 2 theta, so theta is half that, right? At this value of 2 theta, there happened to be planes of atoms that were at the right angle to allow diffraction to occur and give a constructive X-ray beam overlap. Notice that throughout all these angles, none of the planes will allow diffraction of the X-rays. And so it should stand to reason that this information can be plugged into the pattern of intense, which are very high peaks, and low intensity peaks. The pattern of high and low intensity peaks can be used to do a couple of things. It identifies what your unit cell is, feed that into a computer, the pattern. And from that information, you work backwards. From that information comes a 3-dimensional structure of the electron cloud in that crystalline solid, and where electrons are is where X-rays are, and that's how they get the structure. I'm assuming that you know how to do screenshots of different orientations to make this look right, because I've asked for a couple of screenshots.